All right, looks like we're up and running. Got the in the shadows here. Let's see, brighten that up, turn around. Let's see how that is for, that's fine. All right, so more shortcuts and some discussions about material that you've been working with from day one in the semester, which I hope those discussions lend a little bit of a deeper understanding of the things that you're working on. The longer you work with problems, the more you talk about the problems, the more you generally see. And it usually connects to geometry, right? Which is how this discipline, I believe, took off. All right, so let's see, what do I have for a marker here? What do I have? I said I would do this, and I didn't. Oh well, maybe one of these days repetition will kick in and I'll be ready from the get-go. All righty, so let's take a look at the binomial squaring. Let's build some understanding, a little deeper understanding of some things we've been doing. All right, so y equals x squared, should have familiarity with the numerical trajectory, should know that the smallest area, because that's what this is, it's squaring, right? Smallest area you can get is zero. When you square negatives, you get positives. When you square positives, you get positives. But when you square zero, you're smaller than the positives. All right, so let's look at completing the square, which is really putting quadratics into graphing form. And we cut the middle term in half, get rid of that constant that's created, bring the constant in, and we get x minus 5 squared, which I'm hoping you're seeing the squaring, you're seeing the doubling of the middle term. And then if you look at it from the geometric standpoint, you've got x times x and x squared area, x times minus 5 and minus 5x, another minus 5x, and minus 5 times minus 5 is 25. And if we substitute 5, we get 5 times 5 is 25. The linear terms are diagonal to each other. 5 times minus 5 is minus 25. And minus 5 times 5 is minus 25. And I hope you can see the size to size comparison that we've been doing since day one of the semester. The negatives, magnitude, twice the size of the positive. And when you add these all together, you get minus 25. You either get half of the linear or you change the sign of the quadratic term. Either way, whatever shortcut works for you, I hope you can see from a geometric standpoint. And of course, minus 5 times minus 5 is positive 25, and we get a cancellation, 0 for an area. Okay? And that 25 is the y-intercept when I plug 0 in, and hopefully we can see that minus b, 10 over 2 times 1, gets us the critical number in this problem. Now, how did we look at it before? Because I have these discussions all the time. You may only hear them a few times. So let's look at it again. A lot of teachers would probably poo-poo this written statement here, but I think a lot comes from it. All right, we can see that if we plug in a 0, you get a constant. If you plug in minus b over a, the a's cancel, minus b's cancel, and b cancels. So we get this picture, and that's another reason why minus b over 2a is so important. And I think if you look at that, we're splitting, especially if the constant was 0, doesn't have to be 0, but it's the average of the roots. Okay, the average of the roots. And that gives us the key value. And of course, you see it in the quadratic formula, which some of you are making mistakes on still, right? Where b squared minus 4ac, excuse the rotator cuff, right, over 2a, right? And some of you think you're writing that, you're not. You're not extending the fraction bar, and you're writing this, which is not minus b over 2a. Minus b is not being divided by 2a. So see if you can straighten that out for your next test. And one of these days, I'm just going to give you some random numbers. 2x squared plus 5x minus 9. Probably not factorable. Maybe it is 90. But there's no reason that you can't write minus 5 plus or minus the square root. 25 minus 4 times a times c all over 2 times 2, 4. Now I know that this cup shape is centered at -5. So there's a lot of things that overlap here. Right, and we practiced binomial squaring in the last video. We've been practicing it all semester. So a little bit of effort. Right, hopefully you can see 25 minus 5i minus 5i minus times a minus positive t, positive I squared. All right, so hopefully you're seeing this as 5 minus I squared. What does it get you? Gets you 25, square the left-hand side, square the right-hand side, and double the product. All right, so I'm hoping I don't see this much more because you got 100 problems to do. We're breaking it up into smaller segments until we get to that final, but that last 2-hour test is gonna have everything on it. And you should be able to do this quickly, and you should be able to take I squared, which is -1. So you should be able to write 24 minus 10i, certainly in under 30 seconds, without a doubt. And I hope that in your elementary school, you did some 2 rows, 3 columns, 2 times 3 is 6. I hope you did some of that, because this comes from that. All right, so let's look at the tangent. We're starting to do the tangent function a little more often. And where do people stumble? Because you're working with fractions. My understanding is, I already did this before, made a circle, right? And these shouldn't be surprise to you. Those values shouldn't be surprise to you. And so what's the tangent? The tangent is minus √3/2 divided by -1/2. And I hope that you know you can do that. And we've looked at that. Why can you do that? Well, let's look at it one more time, because sometimes students might be thinking about something else and we only do it a few times. And I think you need to see things 4 times sometimes. So minus √3/2 divided by -1/2, same as minus √3/2. I'm capturing this barely. Minus √3/2 times the reciprocal -2/1. And we can see the cancellation, so you could do it right here the next time, I hope. All righty, so where was I? Okay, so this was when the schools merged, girl side and boy side, woman side, man side. A lot of arguments between the 2 departments, the math departments. At least when I first started here in '86, people were like adamant that there were wars over how to do this problem. I don't understand that. I'm for both methods. I'm a peaceful guy. All right, so unit circle, right? But a lot of people teach the 30, 60, 90, and I'll do a 30 degree, right? Or pi/6 radian method, because that takes time to understand what that really means. A lot of folks double the values. Doesn't change the angle any, right? I mean, the angle's the same. If this is 1/2, and this is 1√3/2 here. Doesn't change anything. So I'm in favor of, when working with the tangent, not working with the unit circle. So I would envision this as a 1, a -√3, or -1, excuse me, and a 2. Just double the size, because, division by, working with fractions, just a little bit harder than working with integers or integer statements. So now I can see the tangent opposite the, the vertex, the hinge, what do we want to call it? The reference angle, excuse me, that's what it's called. So minus √3 divided by -1 is the answer to this problem. And so we'll put it on this side, negative and a negative. So that's what you write. Okay, so if you get in the habit of understanding that the unit circle, just double it, and working with the tangent is a lot easier. Okay, so is there anything else I want to say? Not really. All right, so let's go look at a shortcut on something you've been working with now for quite a while. Right, trusty science card following me around here. Taking me more time to do this and put it on the desk, but I do like using it. All right, so let's have a little conceptual discussion and find a shortcut. So you've been writing these in piecewise functions, and if you've noticed, if you are looking at your answer keys, and I know some of you are, which is why you're not going up as fast as you should in terms of understanding, but some of you are looking at it carefully. And if you are, I hope you understand why I'm doing this. All right, if you make $3 an hour and I double your wage, you're making $6 an hour. And if you look at, obviously, the smallest distance traveled is 0. What makes a 0 here? 4. So this is centered at 4.9 right here. And if you look at the slopes, how do you get from 9 to 33? You got to go up 24. How do you get from 4 to 0? You got to go down 4. Well, the slope on the left side for x is this side of 4 is -6. And the slope on the other side, I hope you intuitively understand, is +6. I won't do that. All right, which tells me that if I change my x's by 1, I'm either going up 6 or down 6, depending on which side of the absolute value I'm on. So I decided to go up 6 from 0 to 33. Put 0 in, I got 24 plus 9. I got my y-intercept. That's how I like to graph. I like to nail that y-intercept. And so if I go over one more to the left, I'm going up 6. So 39 is a nice integer answer. And that's what I've been giving you for work because you've got a lot of problems on the test. I can't get you buried in minutia. So this has nice answers. That's fine. And what I'm suggesting is that you can cut down this process to very, very quick, 30 seconds or more, if you understand how to do this. All right. So let's go over and talk about solving for 39 using both branches. And we actually get right here, there's a sign change. Right? When do sign changes occur? Y equals x. Right? When you're on a line and you start to get some negative answers, these negatives turn into positives. And at, the absolute value of 0, we get a sign change. So we're always looking for the absolute value of 0. We're going to get a sign change. For instance, if I have the absolute value of x minus 4, can you see this? Well, the key number is 4 because if I put 3 in, 3 minus 4 is -1. And I'm in that negative vicinity. If I slap it with an absolute value, boom, that number becomes positive. That change becomes positive. Okay. Just mentioning some things. And if I change it here and I solve those branches, let's actually solve those branches. For one thing, I'm not using the marker as much. I gotta write more numbers up here, so it's quicker. Quicker, that little bit of finding the 0 and getting the number that goes with it, and then writing those branches is quicker. And if I solve for 39, +6 and -5 and 5. So, where's the shortcut? If you want to pause the video and think about it, go ahead. I'm just going to keep talking. Well, remember what the critical number was. 4. And what happens if I go plus minus 5 units from 4? Whoa! 5 units backwards from 4. -1. 5 units forward from 4. 9. I think that if I understand this conceptually, and I go back 5 units, I don't have to even write that. Right? Because when I solve +6, this becomes +5. And if I go over 5 units from 4, whoa, I got a real quick way to, you might want to play with that a little bit with this method, because I think you're going to save yourself probably 1.5 minutes of work. That's my guess. All right, so let's keep moving along. Now, factoring, showing, numbers as products. That's what it means to factor. I wish we didn't have the word factor. I wish we simply said, show this difference as a product. Well, in grade school, you probably learned your timetables 2 times 4. But when we wrote products, we wrote it with prime factors, 2 times 2 times 2. And that's what we're still trying to do. Right? So you got to know the rules of writing products. I'm starting to hear people say, rule number 1, what's common? I'm not hearing 2, 3, 4, so on and so forth. Second rule is continue, if possible. The third rule is continue to continue. And number 4 is continue to continue to continue. In other words, you keep going until you got all the prime factors. So what's common here? Nothing. Okay. But I do see a subtraction, and I do see that x to the 4 minus a squared times x to the 4 plus a squared. I usually say plus then minus. I'm going to go back. Okay. Well, if I multiply that out, I don't get any middle terms, and I get what's written there. So that's, rule 2. I continue. There was nothing common. Rule 3. Well, rule 3, I see another problem that's exactly like the first one. So that's x to the 4 plus a squared. You can't factor them. You can't write that as a product. You can try, and I hope you do, but you can't. But you can't write the subtraction of any two numbers as a product, because any two numbers, I don't care what you put in here. I can put 7, I can put 2. I can write that as a product, the square root of 7 plus the square root of 2, times the square root of 7 minus the square root of 2. Okay, so I disagree with this whole practice that we're writing the difference of two square areas. And we only usually put 9 and 4 in here, things that are really nice and simple. But you can write the product of any difference as the sum of the square roots times the difference of the square roots. There's the square root of 14 minus the square root of 14. Those numbers disappear. And I hope the square root of 7 times the square root of 7, you're saying 7. We've certainly done it in class enough time. So if you're not saying that, you got to ask yourself why. Might be that you got to start thinking about this stuff a little bit more. Ooh, the old guy got that. Ooh, the old guy started. Well, we'll just keep going. So we do stop at x squared plus a times x squared minus a. We don't continue. But this one could have certainly said x plus the square root of a times x minus the square root of a. If you ever get in any Olympiad competitions, if anybody's out there doing that, you see that from time to time. All right, so where are we? Oh, we did that. So let's go and take a look at what this one, written as a product might be. I'm seeing multiples of 3. And certainly 1/3 as an exponent. I hope you know what it means. Cube root. And I hope you know what a cube root is. It's a side length of a cube. Again, this whole discipline has evolved out of geometric principles, shapes. So, x to the 6th, the cube root of x to the 6th is x squared. And the cube root of a cubed is a. That's a little easier to see than this. But if I multiply the other dimensions, I get x to the 4th, length times width times height. But we start with the cube roots. And the cube roots of these are written there, x squared, and this is subtraction, so minus a. And then we build the parentheses. Again, this has been stated 2, 3, 4 times. And we've been doing it on probably a month of work of tests. If you haven't figured out how to do this yet, I'm wondering why. So you square this. You square that. Those are always positives. Just like the binomial squaring, they're positives. And then all you have to do is change the sign of x squared times minus a, which I do believe becomes ax squared. And I'll do this one out again. X squared times x to the 4th, x to the 6th is volume number 1. X squared times ax squared is ax to the 4th. X squared times a squared is x squared a squared. Minus a times x to the 4th is minus ax to the 4th. Minus a times ax squared is minus a squared x. I better write that as x squared a. Okay, and minus a times a squared is minus a cubed. Zoom, zoom, you've got it. Now, we've also looked at it, this was addition. Then that simply becomes subtraction. We still get the same thing at the end, except this is a positive now. And these signs just change. That becomes a minus, that becomes a plus. I'm guessing I didn't look. I'm assuming that's true. But it still works out. Right? So, Any subtraction can also be written this way. Is there any reason that I can't just put a 7 in here? And is there any reason I can't put a 5 in here? 5 units of volume, 7 units of volume. I think I can. And if I did, I do believe this will work. And I'm not going to check. So I've got the cube root of 7, it's cube root, right? The cube root of 5, and this is a subtraction. And I got a square of this, which means I'm doing the cube root of 7 squared. And then I'm doing the change of the product. And the change of the product is an addition of, so I'll write it this way this time, 7 to the 1/3 times 5 to the 1/3. Probably a cleaner way of doing this. And then this is going to be addition again of 5 to the 2/3. Let's look at that, 5 to the 2/3, right? Could have written it as the cube root of 25, for instance. Right, so there's no reason I can't do that. And if you want to understand, where it comes from, probably would be taking away 8 units from 27, and there's probably, building this in here somehow. Oh God, I'm such a bad drawer, but you're taking out 8 units, and then you've got all kinds of shapes that probably would explain each of these drawings. But I think computer graphics, we're not going to rely on my artistry. All right, now rules of logarithms. Generally, students do not come out of high school experience having a good feel for logarithms. And understandably, it takes time and it takes practice. And a lot of times sequentially, you go through it 3 or 4 days and push on and memorize some things and never really get into it. So I don't prescribe that. I think we've been talking about these and hoping that some of you are going to be able to follow this. So logarithms are values of exponents. So let's look at our exponential rules. There's 3. M squared times m to the 3rd. It's an addition of exponents. So if you see a couple of logarithms being added, then those parentheses are being multiplied. If I want to look at 2 plus 3, then I'm looking at log of base m of m squared plus log base m of m cubed. So what's the exponent I put on top of an m to get m squared to 2? What do I put on top of an m to get m cubed to 3? So if I was looking at that, it came from m squared times m cubed. And so addition, you're going to see logs added. Division, you're going to see them subtracted. And multiplication, you're going to really see a power to power. So log m to the 10th, could have been base m, could have been written as log base m of m to the 5. Let's get a bracket here, otherwise I really am making a mistake. So let's get a bracket. Let's put m to the 5 and let's square it. And so power to power is what's happening there. And that's the same thing as 2 times log base m of m to the 5. And you need to think about these things. So this 2 is really an exponent. And if I'm multiplying it times another exponent, which is this one, right, then theoretically I am looking at a problem like this. Power to power. All right, now we've been playing with a lot of ln values because I don't think you understand a calculation if you don't have a feel for some of the numbers involved in the calculation. Otherwise, it's just memorizing symbols. So in previous videos, we've looked at e to the 0.72, e to the 1.1, approximately 3, and their negatives, their reciprocals. And I encourage you to dive into those videos if you haven't, because I don't think you can understand this stuff if you don't do it that way. All right, so we're looking at problems like this. What do we put on top of e to get this, for instance? Well, just talked about it a minute ago. Something to the 1/2 is a square root. Something to the 1/3 is a cube root. So we're really looking at what do you put on top of e to get 3/2? And we've been looking at these numbers. So e to the 1.1 over e to the 0.7, 0.4. Okay, 0.4. E to the 0 is 1, right? E to the 1, 2.71. And this is a number between 1 and 2. Okay, so hopefully you can trust it. Halfway there, exponentially, it's less than a half as a number. That makes some sense too. All right, so I'm going to look at the rules of exponents here in order to get our answer of 0.4. Well, I know square roots can be expressed as 1 over 2, and machines work better with numbers than radical symbols. So the evolution, I think, of the computers is allowing us to write things this way now, but years ago. And 9 is 3 squared, and so I hope you can see we're taking half of 2. All right, and what's the exponent we put on top of 3? On top of e to get 3 to the 1.1. So I'm hoping you can see, subtraction, division became subtraction. We start writing our radical symbols numerically, and this is an exponent, and what are you doing to that exponent? Well, eventually you're multiplying, right? So here's our exponential activity, right? Because it's on top of e, and this is base e. So 2.2 times a half, 1.1, and doing the same thing on the right side. I don't have to repeat, basically conceptually the same thing. We see the 1/3 and the 3 canceling. You're getting the 0.7, and there's your 0.4 using rules of logs. Now, I probably would do this problem. I might do it in my head organically, because I'm familiar with all those numbers. But what happens when, of course, you got calculators now, right? But understanding the rules, I still think is really important. So we got square rooting, so 1/2 ln of 23 minus cube rooting 1/3 ln of 11, right? And that's how you would expand this. And if you saw this, I hope you could figure out how you're going in that direction. That's the practice you're getting. And those are fundamental principles. Looks like I'm boxed in here, so I'm going to put the next question. I'll rewrite everything so that I'm here. So I can't get behind that desk right now, so this is history. All right, a shortcut coming your way. F of x equals the cube root of 2x minus 9 plus 1. And I want you to find the inverse of -2. The inverse of that, -2. Of course, you got to understand what the symbols mean, and I still can't see. All right. Let's move that. Let's move this. Yeah, now we've got that question in front of us. All right. Yeah, so you do need to know this is a language. And so this is written, and we don't want to write out find the inverse of f of x and then plug in a -2. And that's what we have been doing. We've been taking this route. We've been saying f minus 1 of x. Well, you got to start with an x. Oh, I forgot to write the 1. So what do? You got to subtract the 1. You got to undo cube rooting. That's cubing. You got to undo subtraction of 9. That's addition of 9. And you got to divide by 2. So that's C. All right, then we plug in -2. And we say -3 cubed is -27. -27 plus 9 is -18. -27 plus 9 minus 18. So we divide that by 2, we get -9. And we plug in -9 to see if we indeed get -2 as an answer. Now, I hope I didn't make a mistake because my brain's a little tired at the moment. And so does -9, does -9 here give us -2? And does -2 here get us -9? We're going to find out. We're going to plug in -9. I like it because -2 times -9 is 18. That number was floating around, 18 minus 9. Oh, minus 18, -27. -27, cube root of -27 is -3, and -3 plus 1, -2. Whoopee! Let's hope I can remember what I started with, because otherwise I'm in big trouble. 2x minus 9 plus 1, I hope. My memory is terrible. But where's the shortcut? Well, what did that process seem like to you when I started here? And I said minus 9. What's it seem like? Where have we been doing that? We've been doing that when we're solving equations. So what I put in here is what I get out over here. Right? So if I want to find what I'm putting in, all you got to do for a problem like that is set it equal to -2 and solve. So what are we going to do? Subtract 1, -3. What are we going to do? Well, we're going to cube, right? The inverse of cubing. So -27, that takes care of that. That takes care of that. Going to add 9. That's -18. That's going to take care of that. We're going to divide. There's your -9. Just a shortcut by keeping your eyes open to what's going on. All right, so I did that pretty quickly because I got some other things to do right now. But hopefully that is, different microphone, or click if you want to switch to a different microphone or speaker. I hope this comes out. Computers and I are not the friendliest. All right, so give some thought to those. And if you can see where the shortcuts occur and you can take them and they're still accurate and you know why, then you are getting a little stronger mathematically. All right, see you in, today is Monday, so I'll see you in 2 days. All right, ciao.